There you go. Okay.
So to use substitution, so we are looking at substitution with definite integrals. I guess I should announce that lesson. So this is one of the other after-school lessons. So to use substitution to find definite integrals, you have two choices. You either compute the indefinite integral and then substitute back, and then just you substitute in your limits. Or you don't substitute back and you change the limits in terms of the new variable, the u. Okay? All right, so let's take a look at that. All right, so here we have the integral from 0 to 2, x e to the x squared dx. What's going to be our u?
X squared.
Yep. Okay, so then we have the derivative with respect to x. So derivative of x squared would be?
2x.
2x. So du is 2x dx. And we don't have a 2, right? So we'll have to divide by 2. So 1/2 du equals x dx. So we're going to replace the x squared with a u, right? And these parts here will be replaced with a 1/2 du. All right, so on this one, we'll do option number 1. We'll just substitute back and the function back, and then just use these limits. Right? So we would have from 0 to 2. That would be we could pull the 1/2 out because it's just a coefficient, and that would be e to the u du. So what would be the integral of e to the u?
E to the u.
E to the u. So we have 1/2 e to the u, and we're evaluating that from 0 to 2. Oops, before we do that, though, let's substitute back. Then we're evaluating. So we have 1/2 e to the u. Notice we're not going to put a plus c. We do have, because this is a definite integral, so no plus c. We got to substitute back. So it'd be 1/2 e to the x squared. And we're evaluating that from 0 to 2. So then our answer would be, I'll just put a area, accumulation, whatever you want to think of it as. It would just be 1/2 times e to the 2 squared minus e to the 0 squared, which would be 1/2 e to the 4th minus, and then this would just be 1. So you can have your answer look like that, or because this would be an exact answer, or if you want to distribute the 1/2, then you'd have 1/2 e to the 4th minus 1/2. If it called for a decimal, then you could plug it into a calculator and get a decimal. Otherwise, I would just leave it like that, okay, as our answer. All right, so this is option number 1, which is substitute back. Right. Option number 2 is change the limits. Right? So u is x squared. So this is the change the limits option. So the change the limits, this is option number 2. Right? So u is, come on, x squared, and we're evaluating from 0 to 2. So if u is x squared, then all we have to do is just change the 0 and the 2 by plugging in. Right? So instead, we would just change the 0 to 0 squared, which would be 0, and we would change the 2 squared to 4. So that means our limits would change. Same integral. I'm just not going to substitute. Oh, I don't need the integral anymore. So I'm not going to substitute back, right? So we've already integrated, right? We had 1/2 e to the u, right? Right up there. So my new limits would just be 0 and 4. So then it would just be 1/2 e to the 0. Oops, excuse me. Helps to put them in the right direction, though. Oops. We got one random line here.
What's the difference between plugging in the current points of integration into the u and then just plugging in the original?
Nothing. It's just a matter of, so the question was asked, what's the difference? There's no difference. You get the same answer. It's just a matter of preference. So sometimes it's just easier. Sometimes it might be that u is something simple and this equation here is something more complex. And so you'd rather just change the limits rather than have to deal with a function with something complex. But really, a lot of times it's just a matter of personal preference. It's just that you have two options. So here you can see it's going to be the exact same answers, right? So we would just have 1/2 either leave it as e to the 4th minus 1, or you could distribute. So you'll get the same answer. There's no difference in answer. It's just the steps are a little bit different. Depends on the problem, and depends what you feel like doing. Usually I alternate. I don't always do it the same way. So all we do is we just plug in these values into whatever x is for u. Okay. Maybe I should put a little note there. So we just plug old limits into x squared. So we're rewriting the limits in terms of u. So for u, it would be 0 and 4. For x squared, it was 0 and 2. Okay, but there's no real difference. It's just really a matter of what you feel like doing.
So that's just plugging it into the before you put it back into the equation.
Yes.
So it really is the same thing.
Basically.
Okay.
Basically. Sometimes it's just a little easier to do it beforehand. Sometimes it makes absolutely no difference at all. All right, so here we have another one. So let's do the substitution first. All right, so what should my u be?
5 minus x?
Yep.
Or,
So then du dx,
negative 1.
-1. And so du is negative dx, and then we don't have a -1, so negative du is dx. Right, so, and we'll do both. We'll substitute back and we'll just change the limits. That way you can see both. So we have from 3, oops. But if I'm substituting, I should leave those off. So yeah, if when you're substituting, don't put those limits back. Just leave them off, or change them, one or the other. Okay. So if you're not going to change the limits, then just leave the limits off. So it would be -1 over u du. And so what would the integral be?
ln.
Yep. So we'd have negative natural log. Oops. It's been a little slow today. Getting extra lines in here. Natural log, and don't forget your absolute value bars of u. Okay.
Because it has to be a positive.
Has to be a positive number.
Oh.
Okay. I probably wouldn't bother to distribute it back and make move this exponent back and make this 1 over u. What difference does it make if it's natural log 1 over u or if it's negative natural log u? Not much of a difference. With the trig functions, it gave us a new trig function and made it a little simpler. Here, the negative doesn't make much of a difference at all. So option 1 is we'll just change it back. So then it would be negative natural log, and then absolute value bar is 5 minus x. And we'd be evaluating from 3 to 1. So we'd have negative natural log. Now the absolute value bars don't make much of a difference, really. 5 minus 3. I'm just going to put parentheses. I'll distribute that negative later. And then minus natural log 5 minus 1. So that would be negative natural log 2 minus natural log 4. And then I'd probably just distribute and leave it the way it is. So it would be negative natural log 2 plus natural log 4. Or maybe you'd want to reverse the order, so the negative a second. I wouldn't change it to a decimal unless the problem asks me to. Option 2.
5 minus 3, 5.
Yeah, so if u equals 5 minus x, then if we have for the 3 there, it would be 5 minus 3, or 2, and 5 minus 1, or 4. And so then you would just have negative natural log u evaluated from 4 to 2. But you'll still get the same answer, right? So it would still be negative natural log 4. That's a, and then minus negative natural log of 2. Oops, that's an absolute value bar. But here the absolute value bars don't really matter anymore.
Isn't it 2
Isn't that the other way
Yeah,
around?
4 to 2. There's 3's on top, so 5.
Oh, you're right. Thank you.
Oh, it does change the sign though.
Yeah, but it could make a difference. Yeah, it makes it right from right to wrong. So this one was my top number, right?
Yeah.
The 3, and then this is the bottom number.
So you-
So yeah, I got to make sure I don't switch those. That's twice I've switched them. Got to pay attention when I'm writing. So then negative natural log 2, and then minus a negative or plus natural log 4. And now you don't need those absolute value bars, but I just got into the habit of writing.
Why is it minus? Why is it? Oh, B minus A? Is that why? Doing that whole thing?
Yeah.
So does that mean 2 would be B?
What?
If you said B or not to be? Then it would be.
I guess technically.
That is what it is.
Yeah.
That is the integral?
I don't understand why it's called an option. Like, I'm really stuck up on that. It's called an option. You're just doing the same operation just before. It's not even an option.
So it is an option. You can opt to do it before. You can opt to do it after. It's an option.
Like shortcuts. Why?
It's
are
not
you
a
putting
shortcut.
it?
It's the same
It's
exact
the
thing.
same thing, but you don't have to do as much.
No,
Yeah.
it's the same amount of doing.
Just filter out of your mind. Just don't imagine it. Just option one. Option one. Say it twice.
Maybe you'll like it better on this one. All right, so this would be a U to U substitution, or you got to do something. You've got tangents and cosines, and so you can't integrate those if you've got more than one function and they're all raised to powers, and it's a quotient. There's no undoing the quotient. So we have to hope that we can do something for this so that we can do a U to U substitution. But we got tangent and cosine. Not exactly inverses of one another. Not a function and its derivative. So that's a problem already. We don't have a function and its derivative. So if you don't clearly see a function and its derivative, try to rewrite it. Try to change its format. All right, so let's change the format first. So we're going to change to have function and its derivative. And a good change is changing to sines and cosines. Sometimes that makes things better.
Change to
Have a function and its derivative. Right. So try changing to sine and cosine. All right, so if we do that,
Sine cubed over cosine to the 5th. And then you could pull out a cos 1.
yeah. Oh, that's not looking better.
Oops.
Good job, Russell.
But let's pull one of the tangents off. Let's try that. Because we have an odd number there.
So then turn that.
Yeah. Let's pull a tangent out. So now we have tangent theta times tangent squared theta all over cosine squared theta. Let's think about maybe the Pythagorean identity. Sine doesn't look so good with the square there. What about maybe one of the Pythagorean identities?
You could change the cosine squared to 1 minus sine squared.
Yep. So we have sine squared theta plus cosine squared theta equals 1. If we divide that by sine, we'd have 1 plus cosine divided by sine would be cotangent squared theta.
We get
You can get
no, not for that. For the
Okay.
For the one.
Oh, okay. Let's see if these look any better. So let's look at all our options here. And then the other one is we divide by sine. We'd have tangent squared theta plus cosine divided by sine would be, wait, what did I just say?
no.
Oh, sorry. We're dividing by
Cosine.
sine. This would be plus 1. Equals, and then 1 over sine would be,
No, you're dividing by cosine this time. You're not dividing by sine.
oh, that's right. I keep forgetting.
Yeah.
Thank you.
Good,
Secant squared theta. We're dividing by cosine, not sine. So there's our identities there. And we want to make something a little bit better here.
So we're gonna change the tangent squared to secant squared minus 1. I don't know if that helps, but we can do that.
We could.
But what's the derivative of secant?
Secant tangent.
Mm-hmm.
Good job.
Wait, 1 over cosine is secant, isn't it?
1 over cosine is secant, yes.
So we have a secant and a
Oh,
secant.
yeah. You know what? Let's separate those.
Go us.
Go you. All right. And you know what? We can leave. Actually, we don't need to break up the tangent.
Yeah, we leave it.
Yeah.
Leave it
Yeah.
for-
Very good. So tangent cubed theta times 1 over cosine squared theta d theta. Now we could change that to a secant squared theta. That's what we need. So now we have now it's all good. So sometimes you try something and that doesn't look so good, and you try something else and all of a sudden, you figure it out. So this would be secant squared theta d theta. Now it's all good because now we can do a u/u substitution. So the one that we used is the fact that 1 over cosine squared theta is secant squared theta. So I didn't think about that, splitting up those quotients. Sometimes it takes you a little bit when you're looking at a problem. I just grabbed these not too long ago because I wanted to go over a few problems like this. So now we know what we're going to do that way. Let's figure out a u/u substitution. And this time we're just going to change the limits and not substitute back. All right, so what's our u going to be?
1 minus secant squared u minus 1.
Tangent theta.
Tangent theta. I like that one.
Because you can just turn it
Oh, we
D-
can do it
yeah.
that way?
You can just change it into secant squared.
Yep. So then we have du dx would be, secant squared theta, d theta. Or, sorry, we're not in dx, sorry, d theta. And so the derivative of tangent theta would be secant squared theta, and that means du is secant squared theta d theta. And so now we're all good. I don't know, watch the time there. So we'll finish up this problem, and then I'll change I'll start a new tape. All right, so now we'll just replace, and let's change our limits as well. I'll squeeze it down here. All right, so we have our u is tangent theta. All right, so that means our upper limit there is going to be, so if u is tangent theta, then we have the first one is going to be tangent pi fourths.
What about tangent squared? It's not just tangent, tangent's cubed.
No, but you can you can leave it in. You can just replace everything.
I think my way is easier.
I don't think so.
It's like a constant.
All right, so here's one where changing the limits makes sense because we're going to end up with, trig functions raised to powers. Here we just have a simple old tangent. What's tangent pi theta? Pi over 4?
1.
It's just 1, right? It's our 45, 45, 90 triangle. It would just be 1 over 1. So now that's our new limit there, 1 instead of pi fourths. And then tangent 0 would just be
0.
0. So those are going to be our new limits there. All right, so now we're not changing back. We're changing the limits to 1 and 0, and I put them in the right place this time, right? Because we substituted pi fourths, we got 1. We substituted 0, we got 0. And so now we have u cubed du, right? Everybody has been replaced, right? Because tangent was replaced with u. The cube stays. And then 1 over cosine, which is secant, is our du. So du is replacing secant squared theta d theta. So all we have now is u cubed du. So what's the integral of that?
1/4 e to the 4th.
Yep. And now you can see why this is a good option. Because I'm not substituting back tangent. So we've changed our limits, and so now I'm not going to have in here tangent 4 theta to plug back into. Instead, we got this. So our answer is just going to be 1/4. I'll distribute that afterwards. 1 to the 4th. Not that I really have much to distribute. Minus 0 to the 4th, which is just 1/4.
Oh, I get it. This is an option.
How did you replace? Oh, never mind. Okay, I see it. Okay.
Okay, so 1/4 is our answer. This was a pretty easy computation here. It wasn't too difficult to plug into tangent, and it's a lot easier than plugging back into the original function. So sometimes it makes it much easier. Sometimes there's not much of a difference. You always have both options.
I see my mistake now in the way because I wanted to change tan squared into secant squared minus 1, and then because you said the derivative of secant is tan secant, right?
Yeah. I mean, maybe that would have worked, but it would have been more complicated.
Are you going to end this one?
Yeah.
Goodbye.
Bye, guys.
Bye, losers.
Don't do that.